Welcome to our NPTEL courses on power quality improvement technique. Today we are going to continue with the PWM rectifier, that will be our third lecture for single phase, and where we have left in our previous class we will start from that is current control waveform, because there is, as you have seen, there is a inner current control loop that will be fast in the response, and there is a outer voltage control loop that will be a slower in a response, and implementation is easier for the for this boost converter. So, if you study little bit of literatures, you will find that several authors have reported several methods for the current control technique. So, we are required to check that what is best solutions or the what is optimal solution from our design. So, for this reason we should put some constraint to evaluate what is the best method of the current control. So, we should be validated to provide the converter dynamics. That is, one of the requirement is that it required to be sufficiently fast, so that it can respond fast in change of load or other dynamics, such as converter always operates near the assuming operating point, because that is where you have the stability. Another condition you require to find that no good condition on system parameters which can justify the approximation is presently known for the basic converter topology. It is well understood in the field of the control system that when converter dynamics are not sufficiently fast, then the quasi static approximation yields neither necessary or the sufficient condition for the stability. So, what I want to say that why it is you have to understood it. Let us say you have designed a buck converter or a boost converter with MOSFET with a switching frequency 20 kilohertz. Now, the moment because of the higher power rating you want to design the same entity, buck converter or boost converter, generally boost converter as I discussed because it is easier to implement, and you want to make it with the GTO, and that is what happened. Instead of the 20 kilowatt you require to operate sub kilohertz level, maybe 500 hertz. So, then what was the stable there, it will not be, but you have changed the value of the inductor accordingly and all those constraint has been maintained, but the quasi static analysis may not be sufficient for the slow behavior, and such behavior can be observed in the rectifier system. Worst case analysis proves stability and should be employed for the simulation, in this case for check that whether it perform best in terms of the simulation term, it will call it is Monte Carlo condition. Now, let us see the same boost converter, how it can be worked in a current control mode or current program control. So, this is your voltage we assume, but this voltage may be like this and the current also will be like this. So, that it does not have a reflections of it into the DC side into the AC side. So, what happened, what you will do, but our discussions will be constrained within this part. So, this is the value of the inductor and it is to be chosen above the critical conduction mode. So, you sense this inductor current and ultimately you know that when it will switch on, the inductor current will ramp on, and thus what happen, you have a V control and from there you will multiply, it is generally of sinusoidal rectified sinusoidal fashion of the double frequency oscillations. So, you multiply it and thus you get some constant Vg into V control, where V control comes from the maybe from the output as well as the sag or the swell. So, then what happened, you asked to ramp on till you know that there is a highest boosting rate. So, for this reason duty cycle is your fixed to some limit. So, for this reason this ramp will be compared with the clock. So, as long as clock is high, so you will get a output here and ultimately you will map with it. The moment current value goes above this within the clock period of time goes above this, it will reset, otherwise clock will drive the MOSFET or the IGBT depending on the rating of the device, and it will be a current control mode. So, you are controlling the ramp, the once it crosses the limit you will turn off the switch. So, that is what we can say, that current program control is a natural approach to obtain, because it is had a inherent short circuit protection, you will not allow current to be very high. Obtain input resistor emulation, ultimately it will emulate the, because you know this is your voltage and this is your current and ultimately they are in the same phase, thus you are emulating this pattern. The peak transistor current program to follow the input voltage, generally it will have a double frequency oscillations, and thus what happen. So, in the before rectification there is no distortion and less THD. So, peak transistor current from the average inductor current, peak transistor current differs from the average inductor current because of the inductor current ripple and the artificial ramp. This is the artificial ramp you will generate from the clock by means of the integration. This leads to the significant input current waveform distortion. This is the one of the problem, because it may not match with the ramp, because you are integrating this. So, you wanted to basically control the rate of change of the current into the inductor, and it has to match it. So, you can be programming like this. So, this is a one way of controlling. So, this is called a current program control, and it has one of the advantage. So, static input, so it is IGTS if you are working on a discontinuous conduction mode, is quite challenging to operate. So, it will be VG L IC square switching frequency minus V minus VG plus M into LA in DCM, but these equations in the CCM will be very much simplified, that is IC minus 1 minus VG by T into M into this one. So, what we can say that at the boundary condition, that means when transition occurs to CCM to TCM, then IG of T of Ts has to follow this logic. If it is equal, then it is in boundary condition, if it is more than, it is in CCM. So, Ts by V 12 Vg by V 1 minus Vg by V, or IC of T equal to Ts by VL MAL by V plus Vg by T 1 minus Vg by T. So, it is desired that IC should be equal to Vg by Re. So, minimum slope compensations we want that Vg by 12. So, this is the slope that you will get. So, you want to have a slope compensation, you act on a slope, thus this method is quite fast than your current mode control, different current mode control. And the static input characteristics of this current programming mode boost converter, we can see that this effective resistance become 2L by Ts, that is your base resistance, and you can see that how it will be changing this value. So, when duty cycle is this ratio Vg by V, and this is the your current Ig. So, if you see that this ratio, if it is less, till this is the envelope of the CCM and the DCM, below it will be DCM, after that you will have the 0.1 of the base value, and gradually at this point around 2 you will have this is to be the base value, and thereafter base value will increase. So, you can control the resistance, equivalent resistance of the circuit, but you see that what if you want to operate at higher resistance, that means at the no load. So, your DCM is quite large. So, for this reason the control will fail, but whereas if you try to highly load these devices, or you load close to your base resistance, then their DCM value is optimal. This is the DCM value. After that you can see that there is a range of the CCM increase, DCM increases. So, it is a challenge to operate this PFC, we called it as power factor correction, in a low in a no load condition for this the discontinuous operation. So, let us see that we have considered that Ig by I peak as a normalized value. So, input current waveform with the current mode control, it is with respect to the omega. This will be sinusoid, and it will be close to sinusoid. If Re equal to 0.1, then gradually it will start to be peaky, 0.33, and you can see like this, and once this happened to 10 times, you can understand that there will be a quite peaky current. So, a substantial distortion will occur in a waveform if you have a higher resistance, base resistance. So, to meet and can meet the harmonic limit if range of the operating point are not too large, that is the condition. So, you can see that you are operated for this R, if it is more than R, then you will find that peaky kind of transition, and THD will not be fulfilled by any of the standard. So, for this we say that the difficult to meet the harmonic limits in a universal input supply. So, it required to redesign the circuit, mostly we change the switching frequency, that is something in your hand, because switches are costly, but if you change the within the network, then generally chips gives the provision to set the switching frequency. Then what we do generally, we require, if you find that ultimately this is the TS is the switching frequency. So, we have to play around with the TS, so that you can keep close to the sine envelope. So, how to do that? This is the hysteresis control, and as I told you that UC 3, 8, 5, 4, 5, 5, 5, 6 are belong to this category. The critical condition mode, and it is the hysteresis control. It will ultimately you got Vg, and you will generate the constant hysteresis band. While discussing the PWM technique, I have discussed details about the hysteresis. So, this will be the hysteresis band. This is the, and you want that this current required to be restricted. Green one is your this current. So, what happened? You got an inductor, thereafter you have switch. So, you start from this point, crosses your value of Vg, then it will touch the this upper envelope, and thus switch will open up. Previously till this point to this point, switch was closed. Then automatically the current will discharge, and assuming that it is a continuous conduction mode, so current will fall here. Again one, it will hit the lower limit, again this switch T1 will be closed, and this ramp will be repeated. So, this ramp is basically the MA. Okay. So, in that way this chip will work. So, this is the case of the hysteresis controller, and there is a one chip FAN 562, that is for the Fairchild chip. So, these will have a different mode of condition. Generally it will on considering that the voltage level of the VG. So, let us go back and understand it, what does it mean by that. So, what happened, you have this voltage VG and current IG will be ramping on till it touch this value, then it will be off, and then it will again touch this value, it will be off, and again touch this value, it will off. So, what happened here, you need not have to get the input, you need not have to sense this current, and ultimately you got a petal like waveform, and if you filter it out, but here filter is a challenge, you require to have a this petal kind of waveform. This petal kind of waveform will essentially replicate this sinusoidal waveform, this one. This is the way it will work. So, ultimately it will filter, ultimately your input current will be chopped like this. So, Australian Sydney Opera, something like that. So, you will get like this. So, this is the way of condition, and what happened here, you require to have this mode, because you can see that inductor current you have to follow and track it like that. Mostly it works in a continuous conduction mode, but here you can go till discontinuous conduction mode, and it can operate in a discontinuous conduction mode for the lower load. So, if you have a lower load, this mode is preferred, for the higher load this mode is preferred. So, let us implement it into the practical circuit. So, you got a EMI EMC filter X and Y, there is a differential mode filter and the common mode filter. I have not shown in detail of it, this is a practical circuit. Of course, there will be a anti-parallel diode. So, ultimately you have this VG here, and from there you will sense VG, and you should have a V control. V control is something that will take care of this, what is the, whether there is a voltage sag or swell, anything that we multiply, and ultimately you will get VR. And VR, once you multiply, you can say that it is a function of Vg plus Kx into V control. So, thereafter what happen, you will sense the current and you will emulate the resistance Rs by the PI controller mostly, and you will compare it. Thereafter, if this multiplications of the IL into Rs is more than the drop, then you are going to reset this flip flop. Otherwise, there will be a zero crossing detector. In zero crossing detector, you will start every cycle and it will be stopped till this op amp input op amp of this point higher of 0.3 is higher than the input of at the op amp 0.2. So, that you are going to reset. This is a buffer, you know. Why? Because it can be, you can easily implement this circuit. Of course, the chip is available to you by discrete components. You know, this is the unity feedback op amp, voltage follower, and of course, you are going to give a resistance of it, because it required to sink a certain amount of the current that has to be provided by the buffer, because these devices cannot provide this much of this. Ultimately, here if you wish, if you see that you are not here, so there is a clock, it is a synchronous. Generally what happened here, it has been reset at every zero crossing. So, it can run in a asynchronous mode also. That is also a of the added feature to this circuit. So, what are the advantage and disadvantage, or the pros and cons of this critical conduction mode control? One aspect is that nowadays it is quite cheap, simple low cost controller for ICs. So, we can fabricate the ASICs, and it is already available for past I think 15 years. So, you can make those easily. Low frequency harmonics are small with constant transistor on time for the boost converter. So, it can be eliminated. Since you can operate into a discontinuous conduction mode, so size of the inductor is quite less, but however, you will increase the peak current, you have a petal kind of waveform. So, there is a increase in the peak current, and thus EMI AMC will be more, and for this reason you can see that we have put that some extent it is something like to stop the bleeding, we put some EMI AMC condition, but where there is a stringent EMI AMC requirement, this kind of design may not satisfy your design purpose. We require to have a different design procedure, we may require to have a soft switching also for that reason. So, increased conduction loss, reduce switching loss, because number of switching because is less, because if you compare this method, here switching is quite high, but where here switching is less. But if switching is less, mean switches are operated at a longer duration. So, conduction loss required to be higher, but MOSFETs generally have lower conduction loss and the higher switching loss, and for this reason it has been preferred. However, this requires larger input filters as well as because you know this will be reflected in AC side. AC is your input, and thus it has to make a sinusoidal, and thus you require to have a large input filter, and thereafter variable switching frequency smear out the EMI current. So, once you have a high DVDT and you got also DIDT, with this interference of the both, EMI will be produced, and spectrum cannot synchronize the converter switching frequency. You will find that some awkward spectrum is also coming for the due to the variable switching frequency. But anyway, we use it very frequently. Transistors is on for the fixed time T on, generally it is a constant T on operation. and transistor is off when inductor current reaches to 0. So, you are always in a critical conduction mode. So, ratio of Vg to Ig equal to Re 12 by T on time as a function of the load, because you have to ramp on, and thus we can calculate the value of the inductor by the inductor voltage balance method. So, charge should not be stored into the inductor. So, Vg t into T on, Vg minus V into T off, if you solve it, T off should be equal to T on, that is what we want, the symmetrical triangle. So, T on will be Vg by this one, and if you can solve it, so solve the controller varies from the switching frequency. So, Ts equal to T off plus T on, and Ts will be 4 Lp by Vm square 1 by 1 minus Vg by V, and thus you can change this switching frequency if required, if to make it a fast and low depending on the resistance. For sinusoidal line variation, switching frequency we assume that with respect to this, we can consider that since it is a 50 hertz and the switching frequency is, maybe you can put it will be in a kilohertz. With respect to this switching frequency, with respect to a particular operating point, we can consider that this Vg is almost constant. That is our approximation. So, it is a quasi static process. So, it is slow, very, though it is 50 hertz is for us it is quite fast, but with respect to the switching frequency it is a quasi static process, and thus the sinusoidal line voltage variation, the switching frequency therefore will be varies as follows: 1 by Ts V square m by 4 Lp 1 minus Vm by V sin omega t. So, there will be a little variation of the switching frequency because of the slowly varying voltage. You may feed it to these applications in avionics. Avionics generally require a 400 hertz supply. So, there also you can fit it and it will work. The minimum and the maximum limit of the switching frequency, thus you can calculate, that is Fs V square m by 4 Lp, and minimum will be V square m by 4 Lp 1 minus Vm by V. This equation can be used for the selecting inductor value of L. So, now let us come to the control part of it. We have said that it is a quasi static process. So, we can apply the control linear control and we can get a satisfactory results. But how much it is acceptable? So, can attain the simple control of input current waveform without sensing the AC input voltage. This is the one of the merit of this previous method, this Petals method. So, Petals method does not require to sense the actual voltage and operates with the continuous conduction mode. So, because it will charge the petal always and it is always a continuous conduction mode. The integrals of the sensed switch current, the charge, is compared with the carrier wave, that is a nonlinear carrier wave, because of this modulation in a cycles by bicycles basis. So, every cycle it will be controlled. Carrier waveform depends on the converter topology. Our discussion is totally depend on the boost converter, and that is the simplest, and you can carry on this for the buck and other, you will find lot of difficulty. Very low harmonics in CCM and wave distortion occurs in DCM. So, we want to operate this in CCM. Peak current mode control is also possible with a different carrier, and that also gives you the steady state stability. Here this is the inductor, this is a nonlinear, this is a control block diagram or nonlinear carrier charge control of the boost converter. This is IS, this is the current through the inductor, and this is Vc and this is Vi. You can see that you sense the current thereafter by the coupling inductor. So, it will be reflected into you, and ultimately there is a switch can on off. So, generally if you will be shorting the capacitor once this output voltages go high, otherwise it will be off. So, this will be go to the Vi. So, Vi will be charging because of this capacitor, and you will compare with this Vg, that is the control waveform Vc, and you will compare it once this Vg by Vc will be reached, you have a turn on. So, you will reset the latch, and so you will be switching on this devices, and this is the way it will work. So, thus what we can say, this is the average switch control because of the capacitor, and ultimately you can integrate over it. We make the controller to regulate the average switch control by integrating the monitored switching current, previous was the peak current, resetting the integrator to 0 at the beginning of the each cycle. This is the way you are resetting this integrator by discharging this capacitor every time. Tuning of these transistors when integrator reaches the reference value. In the controller diagram, the integrator follows these equations Vi equal to 1 by C 0 to T Is by N, and thus what happen Is by Ts N Cn for this discharging operation. So, from there you can say that the effective current and becomes Ig, that is Vg by Re V control, and the rate we relate this switch control input current assuming that it is CCM. So, it will be Is of Tts equal to dt Igt of Ts, the rate of the input voltage to the output voltage assuming that it is CCM will be Vg equal to dt into Vt, and thus we can substitute these equations to find out the average current, that is we have Is by Ts equal to dt 1 minus dt Vt by Re, and from there whole derivations is there. I wish the student to go through the derivation. So, this is the value of Is, and thereafter to generate carrier wave. So, ultimately D will be replaced by T by Ts. If you replace Vc equal to V control T by Ts 1 minus T by Ts. So, you get Vc T plus Ts equal to Vc for the boundary condition, and the controller switch transistors off when integral voltage equals to the carrier wave, and thus Vi dTs equal to Vc dTs equal to V control dt 1 minus dt, and thus Ics by this one, and ultimately Re V control equal to dt 1 minus dt Vt by Is, and this is the value of the effective resistance or the V control. So, what we can say that this is the overall part, this is the integrator reset, is a current source that is coming from this coupling inductor and the capacitor, and this is a V control, and ultimately V control will be reflected as a current source. Once capacitor will be saturated, then by this will be and this will be resetted. This is the average current mode control for this generation of the parabolic carrier wave, or because you can see that this is the parabolic carrier wave. Now, I have finished mainly the single phase power quality problem that has been generated for the diode bridge rectifier for the single phase operation. Now, we shall require to take the industrial one, that is for the 3 phase. So, first we will discuss the problem of 3 phase converters and the kind of harmonic content it there. Because of the time constraint, I leave out that portion of the problem of the single phase, you are well aware of the fact. And now, we shall take out the 3 phase solution of it with the higher power rating. So, we shall first discuss about the 3 phase solution in a different mode, then we shall discuss in last 3 phase PWM converter. Thank you for attention.